Okay, जी, welcome back. आवाज आ रही है जी?
Yes, sir.
Okay. Let's wait for a minute and then we will restart. Okay, so before that we were actually discussing this example in which we have basically two biasing sources. One is VCC and the other one is VEE. And with that we are applying we are using the exact method, and in the exact method we will be actually figuring out the Thevenin equivalent resistance and Thevenin equivalent voltage. So Thevenin equivalent resistance is figured out by shorting all of the voltage sources which are in that specific area. And when we are shorting all of the voltage sources in that specific area, we get RTH, which is the parallel combination of R1 and R2. Then we need to find the Thevenin equivalent voltage, and in that specific case putting all the voltages back in the circuit and applying KVL to the specific loop. By applying KVL to the specific loop, we will be able to figure it out what is the current flowing inside the circuit, right? So the equation which we are going to get, it will be something like this: VCC plus VEE is equal to I into R1 plus R2, or we can say I will be equal to VCC plus VEE divided by R1 plus R2. So putting the specific values, we will be able to find the value of I which is flowing in the circuit, right? And once we have done this, so then what we can do, we can actually figure it out what is going to be the value of ETH. If you see, the value of ETH will be actually the drop in the R2 plus the voltage VEE. Whatever the direction of VEE, it will be figured out, but the ETH is actually equal to the drop in the R2 resistance, and the drop in R2 resistance means we have how we can find out the drop in R2 once we have figured out what is the value of the current which is flowing inside the circuit. So I into R2 will be the drop across R2, and as we are going in the direction from negative to positive, so this means the voltage will be minus 20 volts with that drop, right? So if now we go to the circuit and we see what is the value of ETH. ETH is now equal to I into R2 minus VEE, right? So I is being taken from the equation. I is equal to VCC plus VEE divided by R1 plus R2. And therefore, the ETH we have figured it out is minus 11.53 volts, right? So the rest of the thing is the same. You just put the values back in the circuit and the rest is the same thing, right? Are you with me?
Yes,
Yes,
sir.
sir. सर जी ये एग्जांपल 4.15 भी जरा सा बता दें, ये समझ नहीं आ रही।
कौन सी?
4.15
4.15. ये क्योंकि डिफरेंट थी, बाकी जो है वो आपके जो हमने किया है उसी से हैं। ये क्योंकि इसमें खाली वोल्टेज सोर्स जो था एक एक्स्ट्रा लगा हुआ था, इस वजह से मैंने आपको ये एक्सप्लेन की, वरना अदरवाइज मैं आपको पता है एक्सप्लेन नहीं करता। लेकिन ओके, लेट मी सी।
एक पार्ट भी है ना, वो समझ नहीं आ रहा क्योंकि वो उसमें बीटा की वैल्यू गिवन नहीं है, तो वो कैलकुलेट करनी है।
4.15, yes, this one.
यस सर, ये वाली।
So draw the load line for the network on the characteristic curve, right? So you can draw the line. Is this thing different? ठीक है जी। Determine the DC beta in the center region and define choose point as the Q point. So जब आपने line draw कर ली, right? जब आपने line draw की, तो आप देखें तो ये कहाँ पे है? The beta is determined by IB is equal to 25 micro and VC is equal to 7. तो बीटा आपने ICQ डिवाइड बाय IBQ से फाइंड कर ली। यहाँ पे देखें बीटा की वैल्यू क्या आ रही है, 248।
लेकिन ये आई बी की वैल्यू इन्होंने किस तरह फाइंड की और वी सी की वैल्यू, ये समझ।
IB की वैल्यू इन्होंने जो है फाइंड की है वो आप देखें, IB की वैल्यू जो है आप देखें तो इसका बेसिकली इन्होंने इंटरपोलेशन किया हुआ है इन माय ओपिनियन। जस्ट होल्ड ऑन। ये देखें जब ये जो है लाइन इस पे लाते हैं ना, तो ये इससे जो है स्पेसिफिकली इसके बीच में जो है ये कर्व, तो ये बेसिकली इंटरपोलेशन से आई हुई है।
सर ये आई सी क्यू और 20 माइक्रो एम्पेयर को 2 पॉइंट लेकर इंटरपोलेट किया है ना।
तो यही किया हुआ है ना।
ठीक है सर, सही सही, थैंक यू सर।
ठीक है जी। ओके, सो okay, with this what we have basically 4.19, 4.20, 4.22, 4.23, and we have 4.24 and 4.25, right? So these all the examples, they will be included in the assignment. ठीक है जी।
सर इसका सबमिशन डेट ईद के बाद रखें, दरमियान में ईद भी है।
रोजमीन साहब इधर हैं, चलें रोजमीन साहब ईद के बाद रखते हैं, ठीक है।
ठीक है सर, मैं कर दूंगा, ईद के बाद ही डेडलाइन रख दूंगा सर।
हाँ, okay, so the next topic is current mirror circuit. Right, so the next topic is current mirror circuit. Current mirror circuit. Okay, in this circuit what we have basically two transistors. They are attached in such a fashion that we have two transistors. They are attached in such a way that we are applying voltage VCC. With that we have a resistor that is over here. We call this resistor as Rx, and the current flowing over here is Ix. With that we have a connection point from here to here, and we say that the transistor Q1 is actually identical to transistor Q2. So what we want to achieve from this, that the current which is flowing over here is, let's suppose, I. So what we say that the current Ix will be actually equal to the current I which is flowing in the other Q2. So how this is going to be, let's see. We say that the current which is flowing in the base of the circuit, it should be IB, and we also know this thing that IV is equal to IE divided by beta plus 1. Are you with me? Is this thing fine?
Yes, sir.
No, yes, yes, no.
No, sir.
We have the equation. If you remember, we have the equation IE is equal to beta plus 1 times IB, right? Do you know this equation?
Yes, sir. Yes, sir.
Yes, sir.
ठीक है जी. So just putting beta on a different side, the equation is the same, right? As we
सर इस
also
सर्किट का समझ नहीं आया.
जी
इस सर्किट का समझ नहीं आया.
सर्किट में समझा देता हूँ. खैर ये जो है ये मिरर सर्किट है. So just let me go ahead. So the equation is fine.
Yes, sir.
Yes, sir. Yes, sir.
Okay. Once the equation is fine, so what we can say that in the circuit, if you see, we have the current which is flowing over here is in the emitter leg, the current will be IE, right? Now the current flowing in the base should be IB, and as we have said, IB is equal to IE divided by beta plus 1. But as beta is a big value, so we can say that IB is approximately equal to IE divided by beta, right? Because beta is a big number. Right? So we can say IB is equal to IE divided by beta. Instead of writing beta plus 1, we can write beta because beta is a big value. ठीक है जी? Now in the circuit we can write, instead of IB we can write over here IE divided by beta, right? Now in Q2 there is also a current which is flowing over here is also IB, because what we say Q1 and Q2 both are identical. Q1 transistor and Q2 transistor both are identical. So if they both are identical, so this means the base current flowing in Q1 should also be the base current which is flowing in Q2. So what we can say that this current which is flowing in the base of Q2 is also IE by beta, right? Are you with me? Now at this specific node, which I am marking right now, so at this specific node, if I apply Kirchhoff current law, what should be the value of current which is flowing from here?
Sir,
I
EB
I
plus IEB divided by B.
So this
2
means,
IE divided by
so
B.
this means 2IE by beta. Are you with me now?
No, sir.
No?
Yes, sir.
Yes? No? No? Yes?
No, sir.
Okay. What
No,
we
no.
say that there are two transistors Q1 and Q2, right? And both the transistors, they are being manufactured on the same chip, so therefore they have the identical properties. Once they have the identical properties, so as they are connected to one another, so if the base current flowing in Q1 is IB, so this means the base current flowing in Q2 will be also IB, right? And what we have said over here, that IB is actually equal to IE by beta, right? Are you with me?
Yes, sir.
Right? So the base current is actually equal to IE by beta. So what we have done, we have replaced the base current of both Q1 and Q2 with IE by beta, and they are flowing in their own respective transistors. And if we apply the Kirchhoff current law at the junction point of, if you see, I say, let's suppose I say over here, the junction point is in, this is the junction point, right? So at this junction point, apply Kirchhoff current law. So one current flowing over in the base of Q1, one current flowing in the base of Q2. So what is going to be the total value of current which is flowing in that junction point, applying Kirchhoff current law?
2 IE divided by beta.
Right? So this means the current which is flowing toward this node or here will be 2IE by beta, right? So applying now at this specific point, there is another node, right? At this specific node, the current flowing into this node is IX, right? And then there will be a current which is flowing in the collector of the circuit, which is normally the what we say, this is IC, but IC is also equal to IE. So what we say, that applying over here, that IX is actually equal to IE plus 2IE by beta. Are you with me?
जी सर हो गया
Right? Are you with me?
सर स्क्रीन नहीं है आपका.
Just hold on.
सर जी ये एक सूरत दोबारा रिपीट करें.
Okay, let's see it again. Starting from what we have said, we have said we have two transistors Q1 and Q2, right? The two transistors Q1 and Q2, they are being manufactured on the same chip, so this means they have the identical properties. Now, what we want to see, that if they have the identical properties, So this means whether the current flowing in one circuit will be mirrored in the other circuit or not, right? So for that specific case, we have this combination of the circuit which are being connected in such a fashion. And once they are being connected in such a fashion, so starting from, we say that the current flowing in the base of the transistor Q1 is, let's suppose, from this equation, we have figured it out. IB is approximately equal to IE by beta, right? Is this thing clear?
Yes, sir.
Now, if IB is flowing in Q1, so this means IB is also flowing in Q2, right? So once they are flowing in both, so that specific junction where the two bases are meeting over here, let's suppose this is the point where they are meeting. So applying Kirchhoff current law, so if the current which is IE by beta and IE by beta, so what is the value of current which is flowing towards this junction? So it should be the combination of the two base currents, right? And the combination of two base currents will be actually the sum of IE by beta plus sum of IE by beta. So this means the total current which is flowing towards this node is 2IE by beta. Are you with me?
Yes, sir.
Right? Then we have the other junction over here, which is this one. I have just pointed out. So at this specific junction, IX is flowing towards this junction. And one IX is flowing towards this junction. So it is splitting into two current. One is this one and the other one is this one, right? So this means IX should be equal to the current which is flowing in the collector leg plus the current which is 2IE by beta. But we also know this thing that IE is approximately equal to IC, right? So if we write this equation over here, so the equation will become Ix should be equal to IE plus 2IE by beta. Are you with me?
Yes.
Right?
Yes.
I common current.
So we can say now Ix is basically equal to IE 2 plus beta divided by beta. Are you with me?
Yes, sir.
Yes.
But as we know, beta is a big value, right? As we know, beta is a big value. So this means the 2 plus beta can be cancelled with beta, right? So this means Ix is equal to IE, right? Are you with me?
Yes, sir.
Right? So this means if Ix is
No,
equal
sir.
to
No, sir.
J, समझ नहीं
No,
आई?
sir. Sir, ये No, sir. Sir, ये IX is equal to IE plus 2 IE divided by beta. Sir, ये equation जरा समझा दे, sir.
Okay. If you see over here, coming back to the circuit, right? So what we have, let me show you from the book. Okay. Okay, Ji. So take a look now that what we have basically Ix, the current flowing in Q1, right? And if I say, let's suppose this is node A. Are you with me? Right? So at node
Yes, sir.
A,
Yes,
the
sir.
current flowing towards node A is Ix. The current leaving the node A is IE plus 2IE by beta. And why I have written over here in the collector IE, this is because we say that IE is approximately equal to IC, right? So at node A, what we have this equation which is coming up, right? Ix is equal to IE plus 2IE by beta. Are you with me now?
Yes, sir.
Yes, sir. Yes, sir.
ठीक है जी. And when you do the little bit of manipulation over here, so we get Ix is equal to IE 2 plus beta divided by beta. Are you with me now? And as beta is a
Yes, sir. Yes, sir.
big value, so what we say 2 plus beta is also equal to beta, and therefore we cancel the beta with 2 plus beta. So therefore we are getting Ix is approximately equal to IE, right? And once this is approximately equal to IE, so what we say that if the current flowing in Q1 is Ix is equal to IE, so this means it will also be replicated in Q2, and this current I which is flowing in Q2 is also equal to IE, right? So this means this circuit behaves as a mirror circuit, that we whatever the currents which are flowing in one circuit, they will be actually flowing in the other circuit. Are you with me now?
ये सर फिर तो 2e बीटा जो है ना वो बहुत कम होगा क्योंकि वो i
जी बिल्कुल
x बराबर हो गया वो
बिल्कुल.
तो बहुत कम होगा फिर डिवाइड होके और भी कम हो जाएगा तो मतलब होगा नहीं
तो वेरी
ये होगा
स्मॉल वैल्यू है ना, वेरी स्मॉल वैल्यू,
ठीक है सर जी
right? And if you want to find out the value of Ix, so how we can do that? So looking at the circuit, what we have, we are applying VCC, right? And this VCC, if you see, just so the value of Ix will be equal to, let me just redraw it. If you see, we have this circuit, right? So we have this circuit to which we are applying VCC over here. We have Rx, and then this is being connected to the two transistors, right? Over here like this. So this is Q1, and this is Ix, which is flowing over here, right? Now, and over here we have the grounding which is being connected. So what we can say that the value of Ix from this circuit, looking at it, we can say that Ix is actually equal to VCC minus VBE divided by Rx. Are you with me?
Yes, sir.
If you look at this circuit, right? So if you see at one end of the Rx, we have the potential equal to VCC. On the other end of the resistance Rx, if you see this Rx is connected to the base of the transistor, right? And once it is being connected to the base of the transistor, over here the potential is equal to VBE, right? So this means this VBE is actually directly connected to the Rx. So the drop between the two voltages VCC minus VBE will be actually the potential across Rx. So therefore, we have written this equation over here. Ix is equal to VCC minus VBE divided by Rx. Are you with me?
Yes, sir.
Right? So in this way, we can actually find the value of the current mirror circuits, right? Okay. Any question up till now?
No, sir.
Okay, good.
नहीं
ठीक है जी. Okay. The next thing in the row is basically the current sources. So if you see the current source, so what we have basically there is a voltage source and there is a current source, right? So we can say voltage and current source. So now normally what we have in the voltage source or the practical voltage source, we have the DC source. With the DC source, we have a resistance which is being connected in series to it. Are you with me? So normally if this is the voltage source is ES, so the resistance which is in series with it, that is series resistance R or RS, and after that whatever the voltage which is being at these two terminals, this is being given to the circuit. So this is basically a practical voltage source. So similarly, in the case of ideal voltage source, the series resistance is being taken out. This means the series resistance is negligible. So whatever the potential which is being generated by the source, it is being given to the specific circuit to which it is being connected. So that is the ideal case. But in practical case or in practical voltage source, there is a series resistance which is normally in series to the voltage source which is generating the voltage, right? Similarly, when we go with the current source, so in case of current source, it is basically being represented as normally a circle with an arrow inside it, and then a resistance is being connected in parallel to the current source. So this is basically the practical current source. And in case of ideal, we have only the current source is there, and we say that the resistance which is connected in parallel to the current source is having a very large value. So when it is a very large value, so this means it is next to or close to an open circuit. So therefore, in case of the ideal current source, it is being taken as a current source which has actually a very high parallel resistance. So this is basically the difference between the voltage source and that of the current source. Are you with me?
yes sir
Okay. There is a small thing that which is there. Okay, there is an example 4.30. So just go through it as well, and this is also in the assignment. ठीक है जी?
Sir, it's enough today.
Just finishing up. Just give me 1 minute. And then there is if the transistor is in saturation, right? So we know the transistor can be either in the cutoff region or it can be in the saturation region, right? So if the transistor is in saturation, so what we say that if the transistor is in saturation, so we say we have VCE sat over here, right? Are you with me? Now this VCE sat is working as that we have basically the IC sat which is flowing over here during the saturation time. And we know when the transistor is in saturation, so this VCE sat is actually very close to 0 from the characteristic curve, right?
सर क्या IC0 होगा या VCE?
VCE sat जो होता है जब आपका ट्रांजिस्टर सैचुरेशन में होता है तो VCE sat जो है वो वेरी क्लोज टू 0 होता है. ये अगर आप ट्रांजिस्टर के कैरेक्टरिस्टिक कर्व में जाके देखें तो.
ठीक है सर. Yes sir.
Right? So the VCE sat is very close to 0 at that specific time. So what we can say, what is the saturation resistance of the transistor at that time? So it will be VCE sat divided by IC sat, right? The resistance at saturation of the transistor will be VCE sat divided by IC sat. So VCE sat is very close to 0. So this means whatever the value of the IC sat, so this means it is approximately equal to 0, right? So due to that very reason, the transistor at saturation is behaving very close to a short circuit switch because the resistance is 0. And if the transistor is in cutoff region, so the current flowing inside the transistor is almost 0. IC is 0, and when IC is 0, so this means the resistance is working as a very high resistance, because
Yes sir.
in the denominator the current is 0, so the resistance is working as a very high resistance, so the transistor can be working as an open switch, right? So in saturation